Okay, now we'll switch to English to introduce our keynote speakers, our keynote speaker for today, Samuel Kaski. He's a leading figure in probabilistic machine learning and human AI collaboration. And he has published 120 journal papers and more than 180 conference papers on these topics. This is basically twice as much as I published, so it's like two Nicholas. And indeed, he's worth two professors. He has two professorship positions. He's a professor of computer science at Aalto University and professor of artificial intelligence at the University of Manchester. And he's also the founding director of the ELLIS Institute Finland. This is the second institute in the ELLIS Association. The first one was in Tübingen, and the second one in Finland. This is not an easy feat to achieve, I tell you. It's a quite demanding endeavor. And Sami managed to pull this up, out in a remarkable way. He's also the director of the Finnish Center for Artificial Intelligence, FCI, which is the research flagship project of the Research Council in Finland. He's a director of the Manchester Center for AI Fundamentals and the research director at the Christabel Pankhurst Institute for Health Technology, also in Manchester. He's ELLIS Fellow. He was the coordinator of the ELLIS European project. This was an Nectar of Excellence started in 2020, I think, and that finished last year. One of the first network of excellence sponsored by ELLIS. And he also recently won a ERC Advanced Grant on out-of-distribution deployable machine learning. So this is an amazing amount of achievements. I wouldn't be able to collect probably had I lived twice. And it's really amazing. So please welcome Sami, who will talk about fundamentals of applied AI. Thank you.
Thank you very much, Nicolo, for the kind words. So I really appreciate that coming from you, though I think you might have exaggerated a bit regarding the relationship to your amount of work. But it's very true that when a person turns around 50, then there is a tendency that you would either buy a motorbike or a summer cottage or something. I thought to do something completely different, and I took another professorship at that point. Yeah, fundamentals of applied AI, that's not an established concept. That's exactly why I'm having it as the title is that hopefully you would ask me if I wouldn't explain it. But I'll make your life easier and try to not define, but characterize what I mean. So solutions to the fundamental problems of what machine learning needs for it to be applicable, in order for it to be better applicable, more broadly applicable, more efficiently applicable outside the training distribution, which is one of the grand challenges of machine learning. And that's exactly what I will intend to study in the ERC grant. So some of the things that I am interested in is could we have an impact? I mean, most of us, I believe, are motivated by making a difference in the world, hopefully to the good, with whatever skill sets we happen to have or have acquired during our lives. So I happen to believe that research and development is probably the best problem-solving tool that we as grandiosely as humanity have. So if I as a machine learning can make even a small epsilon-sized improvement into how our best problem-solving machinery works, and it becomes applied across the fields, then that's probably the best I, as a single human person, can do. And I would be very happy to make just a very small epsilon there. Of course, I aim to do a very large epsilon, but let's see what happens. What that could, how that could become deployed in the different fields is something that we call simulation-based virtual laboratories for research and development. I personally have been studying collaborative AI, so how do we build AI, so what does the machine learning algorithm need to have so that it would work well with humans as a machine learning problem? And if we extend that to how should the algorithm look like for it to work well to help us in interdisciplinary problems, that's an even bigger challenge. And then the generalization outside the learning distribution, where it always happens is when we deploy a pre-learned machine learning solution. My argument would be that there is always, in real world, real life, there is always something that is different than in the learning data set. So some confounder, some covariate has different values. And that's why we almost always, when we deploy a system, will go outside the training distribution. And there is typically very few guarantees on our machine learning systems working well. Then in this sense, it is really a grand challenge for this setup that we have in mind, mindset that we have when we build and apply machine learning systems. So as a figure, so how I see these things being related, I'm trying to help characterize what I mean by the fundamentals of applied AI. If on the left we have fundamental machine learning problems or AI problems, this is not a comprehensive list, of course, just a few, then the fundamentals of applied AI is what connects these to the application domains and the interface to the different domains I would call AI for research. So the machine learning algorithms intended to help researchers and research progress in different fields, and health would be an example here. People often talk about AI for science, which would hint at natural sciences. I also mean other fields here. If we have time in the end, I can describe a bit more about the ELLIS Institute Finland, which just launched, and this is from a figure from the Lodge event. There's the Prime Minister of Finland cutting a ribbon, and then there is the previous and next president of the ELLIS Society are holding the ribbon. And I'm trying to desperately keep it up in one end, and then one of the founders, or prime founder, Peter Sarlin, in the other end. But to be slightly more concrete, what I mean by making a machine learning contribution that would be helpful in research across fields. So what are the kinds of things that we would be able to do? So one of the main working horses in empirical science especially, but any design problems, drug design or molecular design as an example here, would typically operate in a loop that is called design, build, test, learn loop. There are various other names for this. So in this case, you would describe the molecules in some kind of feature space, in this case, three-dimensional, and then the researcher would think, what kind of change should I make to this molecule so that it would have more of the favorable properties that I wanted to have, of course, cure that disease, bind to a molecule there, and not be toxic, and so on. And that change is then in this phase space. It is this red arrow here, or sorry, the orange arrow, and then the molecular change would be on the right, described on the right here. So if we can, with machine learning AI techniques, if we can make this loop work better, then we would have made a really big difference. At the moment, the status seems to be that most of the fields, three fields mentioned here, are building their toolboxes separately. On the other hand, there is then DeepMind and a few big companies who are trying to build and sell massive toolboxes. But also in the academic community, there would be the opportunity of building methods that I'm calling AI methods here that would be more generally applicable if we can solve some of these fundamental challenges of applied AI. And now if all of this is happening based on simulations, if we run the design, build, test, learn cycle in simulations first, then we can also ask the more advanced question as AI researchers, can we develop the tools that would help run those loops based on simulations so that the researchers of that field would be able to run their simulations more effectively, more efficiently, and then go to the real world and try out their molecules, for instance. This is what I'm talking about here, and there is an obvious scale-up advantage here if we can have techniques that are applicable across the different fields. So in general, I'm studying two big questions. So the first one is, we have typically unknowns in the model, or even the whole model can be unknown, and then we would have unknowns in our goals as well. I'll get back to this latter one, which may sound a bit more esoteric, but I'll get back to that slightly later. But unknowns in the model, I assume this is something everybody here is very familiar. People would just formulate this problem in different ways. I've now chosen one, but the principles I'm talking about are not specific to this specific formulation. So if our task is to learn unknown parameters from data, a Bayesian would then say that we need a prior distribution for the parameters and a likelihood, and then we could, in principle, and the likelihood is essentially our model, and then we can compute the posterior distribution of the things that we didn't know, and then do decision making based on those. That's of course standard Bayesian data analysis textbook stuff. If we then need to collect new data, we can apply so-called Bayesian experimental design in this experimental design loop that I described to choose the next thing to measure. So based on our model, we would choose our design, we would run an experiment in simulations in the real world, we would observe the outcomes, we would update our beliefs of the parameters, and then we would have a new model which contains these updated parameters, and then we would run this cycle. That's roughly how it would operate. And now here we have a very nice resource, actually. No need to read everything here. I just wanted to point out that the Wikipedia, in this case, it happens to be really to the point. So on the left, you can see the Bayes rule. I don't see the laser working, but I probably don't need it. So the Bayes rule for updating our beliefs, we can compute predictions, also marginal probabilities, and then for the experimental design, we also need to choose what our goal is. And it is described here by the utility function u, which describes how good that particular design that we pick is given the observation we get. It could be that the particular molecule, for instance, then turns out to bind very well to the desired molecule, which is hypothesized to help cure the specific disease, for instance, right? So we would define our utility function, and if it would have uncertainty because of the parameters that we don't know, the theta. If we then take average mean over the parameters that we don't know and maximize that, we would be maximizing our mean expected utility. That's the principle. And now if our utility, in the most general sense in science, if we choose our utility to learn maximally about our model, the things that we don't know yet, our utility would be expected information gain about the parameters in our model. That's what these equations are saying, right? And this really, I am recommending this page to all my students. This is a good way to get started if they know the notation, and then we can start talking about what would we do scientifically next. Of course, what this does not say, that the problem is solved. I mean, yes, we can write these equations, we can write these integrals, but unfortunately, usually we can't compute them. Even if we can, it would be so incredibly slow that we wouldn't be able to use them in the solutions in this experimental design loop if we want to get the results out any day soon. And this is where the neural computation, the latest advances in generative AI actually come in very handy. There's one specific technique which is rather kind of blunt. It's a very simple, conceptually simple idea. It is that if you can compute whatever you need to be predicting later, if you can compute a set of solutions, set of initial states and set of outputs beforehand, and then just learn a neural network or any predictor, but neural networks happen to be really powerful for this, that maps the inputs, initial states, to the outputs, whatever you need to do. You need to do a lot of computation beforehand, in particular if you want to cover all possible setups that your experimental design system in this sense, or any decision-making system will encounter. You will need to do a lot of pre-computation, but on the other hand, online computation is very, very fast. So it's a very blunt instrument in this sense. So if we can pre-compute a lot beforehand, essentially have a foundation model for that task. So foundation model meaning that you would have a model that captures everything there is in the data. Now in this case, simulated data that you construct yourself. Then you can use it to do amazingly fast predictions online. So what does this have to do with Bayesian experimental design? In the experimental design, the decisions that we are doing in the loop at every single step is how do we move in the three-dimensional molecular space that I showed you earlier. Which thing do we measure next, right? Now if you would do pre-computations on the trajectories of different choices that you made along a trajectory and the outputs that came, given your model family, which would give you the ground truth in that simulation, and if you do this in a representative set of cases and learn a good neural network to approximate that, well, yes, it would give you the output of what should you measure next given all the things that you did before. Rather simple idea, and 10 years ago, and especially earlier, I would have thought that, well, that's madness. It's never going to work well enough, and we will not have enough computation to do this well enough, even if in principle it would. But amazingly it does. Of course, what we lose is that we typically cannot have guarantees, statistical guarantees on how good the trajectories are for any specific case. But on average, empirically evaluated, they are amazingly well, given that we wouldn't otherwise be able to do anything. The computations are simply too heavy. And the decision on what to do next, in this case, it would be called a policy. So given your state history so far, what is the next action you should take? That's called policy. Now here I want to give credit to my amazing PhD student, Daolang Huang, who has been the key author in the couple of papers I'm describing now. He has been studying the problem with me for a case where we need to really rapidly choose what to measure next in these kinds of loops. We also would need to really rapidly infer on our model's parameters, which is another really big integral, in order to decide what to do next in this loop. And then, furthermore, if our goals change, or if we didn't know our goals in the beginning and we gradually begin to understand what our goals really are, how would we then change the goals on the fly? These three questions. And what we did is essentially what I said. We pre-compute a lot of solutions, then we learn a very flexible neural network. In this case, a transformer is really good at this, and then that maps the predictions into two different outputs. One is what should you measure next, and the other one, what would the posterior distribution of the unknowns look like given these choices that we have made so far. In principle, simple. In practice, of course, there's lots of engineering and math behind making this really work. As a result, we have a model or algorithm, which is able to do online inference about the posteriors, about predictions that we want to get out of our models, and is also able to choose the next thing to measure to maximize information about the posterior, maximize information about our predictors, and flexibly choose between those two, which are slightly different cost functions or criteria or utility functions that we might want to do. Earlier variant was last year, where we asked the question that what should we do so that we can fast enough switch our utility functions. And this year's paper was about this, how do we combine acquisition of new data and the inference. That's as much as I thought to tell about the first question, what to do with the unknowns. So now it is possible to do approximative inference given on the unknowns, whether they are predictions or parameters of the model. And next question is about what to do with the unknowns in the goal. And I've noticed that this is a bit outside our normal mindset, which I think is a bit funny, because when we read any memoirs of great scientists, they seem to be always emphasizing that choosing the right problem, that's the key. Of course, we need to also solve the problem well, but it really is the crucial question on how do you choose the problem. And everything I said up to now is only about how do we solve the problem well in a certain sense. And that's what most of my colleagues, including me, have mainly been doing, kind of asking these questions of how can we do things more efficiently. And even if I've now started asking, and many colleagues as well, have started asking, how can we, AI researchers or machine learning researchers, how can we help scientists in other fields with our techniques? Still, the techniques are more about the practicalities on what to measure next instead of what should we study next. And don't worry, I'm not going as far as telling anybody what should they study, but it would be very nice to have tools that would help us ourselves refine what we in our research program actually are aiming at and which problems might be solvable and so on. I mean, that's what science mostly is about when we are trying to find the solutions, isn't it? All right, in this loop, and that's of course, that's really hard problem. I don't claim to have anywhere near a universal solution to this. But there's one thing that I believe we can do. And it is that if we are thinking of a problem where we have this kind of a loop, but our utility function is not carved in stone. So what we want to get out of this, we might be thinking of several different things. Having good, if I'm thinking of the drug molecules, so now some researcher in pharma might be thinking of a specific disease and has a hypothesis that this particular type of a drug might bind very well to that particular protein which has been implicated in this disease. But if it doesn't, typically they wouldn't go home and from scratch start thinking of another molecule for that problem. They would quickly consider that, well, this seems to be effective for something. What is it effective for? And this is called drug repurposing. So that would be an instance of where our goal is not set in stone, and we could very validly switch our goal during the project. There's of course plenty of examples. But now if we have this kind of a loop, and we have a scientist running this loop who has hypotheses, has prior knowledge, and has thoughts on where they want to take this research project to. And ultimately we of course have somebody who pays the bill and certainly wants to have some say to where this loop is taking us. So now me as a machine learning scientist, I can of course set up a system that actually asks the scientist. And now fully aware that I wouldn't myself be able to tell kind of some uncertain knowledge on what I'm actually going to solve next. It's very fuzzy in my mind when I'm doing the work. But I do have some clues. And now the system could ask. There's a separate question on how it should ask so that it's maximally effective for this, but it can ask. That's an element that we too seldom consider. Right, so what would these questions look like? So this is the simplest thing I can think of. So now in the drug design case, how they think of this, at least in some part of the pharma, they think that there is some scoring functions that score molecules for different purposes. One would be that it's not toxic in humans, one is that it's not toxic based in animals. Some of these would have been estimated based on data on toxicity in humans and animals, for instance. And there would be data about how well that particular drug is predicted to bind to a certain type of protein, for instance. Those each would be a scoring function, and now you could consider some kind of a combination of these scoring functions to be your utility function, total utility function. You just don't know the weighing of this mixture of these in a logarithm scale here, a mixture of these scoring functions. And then that's the question that the machine learning algorithm needs to identify while asking the human a minimal number of questions. In this particular simple case, how the questions are asked. So there's a generative AI algorithm which takes the current scoring function, produces a set of candidate molecules, and then gives them to the pharma researcher, who then picks up those ones that seem to be going to the direction they want to go. This is a rather easy thing to do if there's a reasonable small number of molecules. They might also kind of paint in the molecule the part which is the reason why they think this is interesting and so on. But this is a separate design challenge on how should the interface work. Now, we are not assuming here that the humans are infallible. That's the question that I often get. Kind of, does it make sense to assume that we know everything? Of course not. But here's the simplest thing that we can do about that. Let's assume that the human may make errors, and the errors for each type of molecule will depend on a parameter of a Bernoulli distribution that describes how likely they are to err here. And then we can have a more sophisticated model that's trying to capture the relationships between the molecules here. In other words, how the knowledge base of that expert relates to the errors they might be making for different kinds of molecules. Okay, now this is a model. This is a probabilistic model. I know how to run this. And Nicola hopefully knows how to compute bounds additionally on this. So I've noticed that it's hard to find students who would be interested in working on this because our mindsets seem to restrict us in a funny way. Because to me, this is few people working on this, massive opportunity immediately there if I can contribute, right? But students often in the beginning might not think in this way. I remember when I was a student. So that's why, I mean, those who come from human-computer interaction, they typically would think that I'm stereotyping now badly, but many of them would be thinking that, well, probabilistic modeling, yeah, you are putting a lot of power or time into some side issue details in math, which cannot be important for the interaction. And often they may be right, but in this particular case, they definitely are not. On the other hand, my machine learning students are thinking that, well, human-computer interaction, it's some hand-wavy field where they don't even justify, or at least it's not rigorous, and I don't want to have anything to do with that. And of course, both of them are wrong, badly wrong. I mean, it depends on what approach you take, whether it's rigorous or not. And what could be more important for us humans, to have systems that work well with us humans. Okay, that's why, anyway, that was the preamble. Because of that, we wrote a paper trying to convince people, make it maximally easy to understand why we actually need to put both things into the same models, the insights about humans and the rigorous machine learning. And we took a naive example where the young Newton is trying to figure out the law of gravity, and then a naive example where what would have happened if the young Newton would have grown up on a space station? What would our law of gravity look like then? And now, because the apples wouldn't necessarily fall. So now it's a naive example, but just trying to highlight that if we want to help the person, researcher, in this case, the young Newton, figuring out his first law of nature maybe, we actually have to put the human into our models. Even if, as natural scientists, we might think that isn't it kind of several hundreds of years science has tried to take the observer outside our models to make them more rigorous, except maybe in quantum physics. Now, are you serious now putting the human back into the model? Well, if we are going to help young Newton here, we have to. Because, of course, the important variable here is what does the young Newton know and what would he benefit from in this particular case. Of course, we don't need to give out the objectivity, but in this formulation, what the objective laws of nature are simply integrating out the nuisance variable, which is the particular observer's knowledge about the world, which should give, I mean, that's an impossible integral to compute, but it should give us something like the current law of gravity. So if my task is to develop machine learning methods that help the scientist is the user here or the expert. If traditional setup has been that the scientist makes a design change, measures something in the world, and observes the outcome, develops the theory further, and designs the next experiment. So then my task would be to put an AI assistant there who is making recommendations one way or the other, and then observes what the expert did with these recommendations and tries to learn more both of the expert and the world. So for it to succeed in this, here's another magazine piece that we wrote to make this more understandable. It needs to have some model of how the human is doing the planning in this decision-making task, based on which it can recommend, and the data for that model is the observations of what did the expert actually do. A very concrete and actually turns out to be very non-trivial task is trip planning. So when I was thinking of coming to Rome now, kind of my task, unfortunately I didn't get this far. My task was I have a bit of a flu, I need to survive, I'll maximize my sleeping time, and the other objective, which is to get some Keynote cooked up before my time is out, and then I'm going to sleep for the weekend. That was very simple. But often when I would come to Rome, I would be thinking of have some budget of time, money, and so on. I would be thinking of which places will I manage to visit and which friends will I manage to visit. And there are dependencies between these. And it's of course a traveling salesman problem once you fix many things here. So now this is an instance of where I would definitely need this kind of a helper. Because when I start doing that planning, then I realize that, oh, I actually didn't take into account this and that and so on. It's impossible to write down my objective function and then just to maximize it. Because my objective function would change as I see what is available, right? So now, what the recommendations here are that given your current plan for the trip, it seems that you might want to consider, this is actually now from Paris as you see, but I mean, I didn't change the Louvre here, I'm sorry about that. So might you be able to go to Louvre as well, or would you like to? And then the person might also be put in additional places there, and then the system will solve the traveling salesman problem and so on. Now the system will make these small changes, one change in the trajectory, and it turns out that compared to an unassisted agent, meaning the human, these recommendations as a number of steps, one step is to make a recommendation and see what the user does. The user is able to improve the objective function quicker than by doing it alone. That's what the graph is showing here. If the user is willing to let go completely of the control and just let the AI plan based on what it has learned, so the AI wouldn't ask the user, then the objective will improve even quicker, but the user would need to lose control. A few of us probably would want to. And this works better than the alternative straightforward algorithms. But again, we have the problem that if we want to do these kinds of things for any non-trivial task, they are way too slow. So that's why we asked, can we amortize also problems where we ask the human? And we humans seem to be really bad at giving absolute judgments. How much do I value this particular food, for instance? Whereas we are much better at assessing, do I prefer this or that food, right? So if we can ask people these relative preferences, then people will be able to give better inputs. But on the other hand, the machine learning problem is harder. But it turns out that with very similar architecture, we actually can amortize also the loops where the environment is the expert. We are asking, do you prefer this or that, with minimal number of questions. it's 10 times faster with comparable performance if we do the amortization. And this was in iClear this year. And still about this, I haven't touched on two really crucial problems. This is the first. I just said that so far we have been assuming that the humans would make errors, and we just assume the errors to be independent, and there's some parameter for its kind of decision on how likely the human is to make an error. Unfortunately, we are not quite that simple. We have all kinds of dependencies in our mind. And it turns out that even in simple tasks like preference learning, we actually have to take those into account. So the question is, in modeling terminology, so cognitive science, psychology have a lot of prior knowledge. Can we take that prior knowledge, relevant parts of it, and improve a lot on the assistance that we are developing? And the answer is yes. So this is a collaborator with the senior cognitive scientist, Andrew House, which has been very enjoyable. So one instance, I'm not going to details on these, but one instance of these kinds of nasty things is that if we are picking in risky choice scenarios like betting or investing, we typically would need to trade off between the value of each event and then the probability that it is favorable to us, right? So we can draw these kinds of equipotential surfaces where the expected value for us is the same, right? So now you might think that it doesn't matter where we are on this curve, we would be choosing, our choices would be preferences of these over something else would always be the same. But it happens that if we show people 3 instances, so we add what is called a decoy here, everybody would start favoring B. And now there's lots of literature in cognitive science on this and related problems, which we could in principle take, but then there's really much of that. We were just chatting with Nicola about this, that can the ChatGPT research actually solve this for us? Maybe you could try. Does this work? I guess it doesn't yet. But we can build a model based on this, and now I'm giving one slider of how I understand the principle that Andrew and colleagues have been developing in cognitive science. So they and I would very much like to have a principle for how do we derive a good user model for any task, right? Of course, then details will be different in different tasks, but if I understand this principle, then I could in principle do it and ask, can I amortize it and so on. So this assumption I would agree with, and it's called computational rationality, or assumption underlying so-called computational rationality. So the assumption is not like in economics, for simplicity, the assumption often is that people are rational, which took for a long time for me to understand what is that claim really about. It means having infinite resources. And of course we don't have infinite resources, come on. So I need to get the result maybe today, maybe a minute ago. So but instead, if we assume that humans act rationally, given their constraints and limitations, including the time available and any cognitive constraints, these I would agree with. The problem just is that we don't know those limitations and the constraints. But in particular, in principle, we can learn some of those. Some are hardwired, we can pick them from cognitive science, some we can learn when the system is operational, and we don't yet know when is the system identifiable, when can we learn these. But there are cases where we can. And once we, at least in principle, the forward problem here is reinforcement learning. So learn what would the human do given the constraints. If we knew the constraints, we could compute what they do. And now if we observe behavior, we could now compare those predictions to what the human actually did. And if they don't match, then we ask, how do we need to change the constraints until we get there? So this can be done, but it's incredibly slow. But fortunately, we can again amortize. It seems that this is becoming like a silver bullet now. Of course, it's not, but we can do plenty of things with it. And it turns out that if we take this kind of choice model a risky choice model, choosing hotels, for instance, where people are given more than 2 instances, this works much better than the existing alternatives. Skipping all details here. How am I doing with respect to time? Maybe 10 minutes or so. Yeah, then I'll pick up the other big thing that I didn't cover at all yet. So far, I've been treating data from humans just as kind of independent observations as we would think of observations from the nature. Kind of passive observations. And unfortunately, we humans tend not to be passive, meaning that we typically have an agenda, we have a goal, and we design our actions according to the goal. So to demonstrate that this is really crucial and we have to take this into account, even in simple cases, I'm showing a simple example here, which is now a game that the AI is playing with the human. And the game is to maximize this function, and the AI does not know the function values. The human sees this function, but the AI can ask 1 point at a time, 1 x-axis point at a time, then the human gives an answer, the AI infers whatever it wants, and then this game proceeds until the AI finds the maximum. Black box optimization, maximization of a function. So now here you see 2 points that the AI has queried, the user has given these circles here, and now the AI is asking a 3rd point here at xt, and the user has a slider with which the user can give an answer. Right? Seems simple. Now, when I'm the user in this experiment, I would think I wouldn't be fitting any functions, but I would be assuming that the AI is probably, if it's clever, it has some uncertainty estimates, which are tighter where it has observations, and then it's probably assuming continuity and smoothness if it doesn't know more, right? Because nothing else is told. Now, if I would give the answer on the top right, if I would give the answer at the function value, and by the way, nobody told the user that you have to give the function value. Of course, the user wouldn't be needed if the user always gave the function value. So then probably what would happen with the uncertainty interval, which is the light blue here, would be something like this. And as a result, it would be very unlikely, given the current estimate, that the actual optimum, maximum value of the function, because it's outside the confidence interval, would be where it is, right? So now for the AI, it would need to ask me a lot of questions in order to actually find the optimum. On the other hand, because I wasn't told that I need to give the function value, I could say something like this, which can be interpreted like, well, it's very close to the optimum. Well, it's feasible to think that it would be rather high here, even though it isn't. But I mean, that's what you need to hear in order for you to proceed, right? That's what we haven't studied this with people playing against each other. But I believe something like that would happen if people were playing with each other. So your task is to try to help somebody else find the maximum. Of course, you would do something like that, right? Or at least this is how I think. But of course, now it's possible that others don't. That's why we did a small-scale user study. So as a function of the iterations, how many questions the AI asked, how quickly did the score, which is a measure of how well you are finding the optimum, it actually improves much quicker than if the system would be giving the right function values. Which is not surprising based on what I said, but that was just a hypothesis. This is small-scale confirmation of that. And it turns out that the optimum is found quicker if the more the user actually, the more the user deviates from the function value in the answers, except if they go completely bonkers. Now, what I take from this is that we humans seem to be very kind of ingrained. It's ingrained in our thinking that we are thinking in terms of purposes, goals, and purposes of goals of others we are working with. And if we are building AI assistants, then those are very much creatures that will be working with us. So it probably would help a lot in human collaboration with the agents, assistants, if they would be able to take this property into account. It's called the theory of mind in psychology literature, so that we attribute to each other that the other guy also has a mind. This is of course not obvious, but I mean, if we do this, then we behave differently. It would make sense that the AI would also do this and would behave differently in return. All right, for these science parts, I'd like to thank my team and many collaborators who I'm not listing here in the interest of time, and just saying that the ELLIS Institute Finland, which launched this year, I showed the launch event photo. It launched in November. Funding comes from the government through the Ministry of Education and Culture and private sources such as the Foundation PS of Peter Sarlin. And it's a collaboration of all Finnish universities. All of them wanted to join so that the new PIs that we are hiring, they are at the same time ELLIS Institute PIs with the main affiliation, and they get tenure track professor position in one of the Finnish universities. And this is what I thought is needed so that we can make maximally attractive offers, which is the main goal here. And this is what I believe we in Europe share. I would be happy to give some ELLIS speech, but Nicola said that everybody here knows about ELLIS, so I'm saving your time on that. So what we started with, I'm skipping a few things, started with is launch the PI call. We hired 10 really amazing researchers, most very young, but that's exactly when they need to start in order to have enough time to become really good. Now we have the second call out. We are going to hire at least 7 more. So if you know very good candidates, please tell them. And if something like this is going to happen in Italy, very happy to collaborate. And in any case, with your excellent scientists, of course. Thank you very much.
Thank you. We have time for questions.
Thanks, very inspiring talk. For having human in the loop, it is very much also important to be capable of communicating with the user and with the. So you have planned to use any XI techniques in your pipeline?
Yes, my main contribution is to formulate these problems as probabilistic modeling problems, because once I have done that, then the machine learners who have similar skill sets than I do are able to contribute. But we are working in this problem as in any problem, in the pharma problems, for instance, then of course we work with the best people we can get our hands on who are working in pharma. But likewise, in the human-computer interaction aspects of the interaction, we are working with people who are really good at that. For instance, Antti Oulasvirta is one of associated faculty in the ELLIS Institute Finland, and he's an advanced grant holder in that field in human-computer interaction.
More questions? So maybe I'll ask one in the meantime. So a lot of the things that you were saying are kind of dual. So there's AI is adapting to humans, humans are adapting to AI, AI is steering a human behavior, humans are steering AI behavior. So in a sense, it's a system, especially if you have more actors, and you may want to ask what is, if the system is going anywhere. So there's kind of, is this actually a dynamical system of agents that influence each other, reaching some kind of a good equilibrium where things work well for everybody? Have you ever tried along these tried to think along these lines?
Right, yeah, really excellent question. And the much nicer put than the alternative which I often get is that, isn't it threatening that the AI can now influence us because of this, what you now said? And of course it can, and it is threatening, and we need to do something about that, but yes.
For at least a few years. So yeah.
Yes. So but yeah, that's exactly the angle that I would also take, is that what I can contribute to is how can we do good things with these different assistants? And now, of course, you can analyze the dynamical system. It's typically difficult, but if you make the assumption that they are both POM-DPs, then it would be a so-called IPOM-DP with certain representations. And you may be able to have some convergence results. Typically, you have to assume more in order to have them, but this is a question that can be asked and potentially answered. So in that sense, it's already well defined, and I agree and like it. In most cases, I think we humans are really good at trying to, it seems at least, we are really good at kind of grounding the discussion really quickly before it goes to kind of, did you think that I thought that you thought, and so on, which of course it would never end. So we seem to be operating only on levels 2 or 3 maximally, meaning that, did you understand what I said, types of questions. And if not, then I would say, well, let's kind of step back a moment. I'm not sure I understand what you are saying. So those kinds of techniques we would apply. And of course, we could install those in these systems as well to avoid the eternal loops. But then that matches to the 2 agents already, right? Now, when you are thinking of several kind of group work, really, that's what I hinted at in the first slide, which I think is incredibly interesting, is that can we solve better interdisciplinary problems or can we build assistants that would help us in interdisciplinary problem solving, where we seem to have really, really few tools at the moment. And that is an open question.
Thank you. Yes.
Thank you. Very nice talk. One common question I would like to raise is how do you think it's somehow reasonable in the long term, this hypothesis about the rationality of the user in this interaction for finding implicit tacit goals, in a sense that there is in the interaction between the model, the retraining, and the user, there is a mutual influence. Now, I wonder to what extent a fixed linear model can actually work in a real setting.
Right. Yeah. To start fixing a potential misunderstanding, we are not assuming any fixed linear models. We have learning systems which can be also nonlinear. But if I understand correctly what you're after, that's very true, and an important problem is that once we work with assistants or work with other people as well, of course we kind of implicitly start delegating some of what we do to the other party, because that's why collaboration is so efficient. And of course we will do the same with our AIs. And for instance, my memory is suffering because I have notes-taking tools and have had them all my life. It would be impossible for me to remember a phone number now. I can remember kind of theories, but I wouldn't necessarily remember the exact instantiation of the theory, simply because I can look it up, right? So these kinds of things are going to happen, and I think the answer is that nobody really knows where that's taking us. And now we can either try to be very conservative or very lenient, or then find a good mixture. I think the good mixture would be more efficient for us. Where I think we need to pay attention is kids. If they haven't developed the internal thinking tools, then these can really be dangerous potentially. But I don't know enough to say anything about that, unfortunately.
Thank you. Any more questions? Okay, let's thank the speaker again.
Thank you.